Hello, today we are going to talk about fluorescence. Even if this is not widely used in experiments, in research, in different disciplines of research, biochemistry, bioorganic chemistry, pharmaceutical chemistry, or other branches, this is a kind of approach that cannot be exchanged with other methods. It is actually effectively used in cell experiments to see the effects of different molecules and some other agents. So today we are going to talk about fluorescence. Here we go. Okay, what is fluorescence? It is the emission of light from matter that has absorbed light or other electromagnetic waves. Fluorescence is a type of luminescence. It's an emission of light after absorbing radiation. It occurs very rapidly in nanoseconds, and it is common in chemistry, biology, and physics. The point that we have to keep in mind is that fluorescence is the emission after the absorbance of electromagnetic waves, which ranges, let's say, from 200, let's say 700, 800. And in fluorescence, we usually see the effect of close to visible light UV range. Starting from 200 nanometers and the visible light ending at, let's say, 750, 760 nanometers. So this is shortly about the fluorescence. And here we can see fluorescence is the emission of light from matter that has absorbed light or other electromagnetic waves. In our previous lesson, we talked about atomic emission spectroscopy. And in atomic emission spectroscopy, uh, we said the same amount of energy, the same amount, the same type of electromagnetic waves that are absorbed and that are emitted during the during the atomic emission spectroscopy. And here, the fluorescence differs from atomic emission spectroscopy method, which means in fluorescence, in this process, the energy between the absorbed and emitted differ from each other, and the mechanism is the same. The energy is absorbed, and electrons move from the ground state to the excited state, and some electrons turn to vibrational energy, spent and lost as vibrational energy as indicated here, and the remaining amount of energy is emitted. That's why the energetic level of emission is always lower than absorbed level of energy in fluorescence. Okay, we are going to talk about these things more in detail in the coming next pages. And this is about different color sources. The source of different colors results from several excited states of electrons. As we talked in our previous lessons, in atoms there are many electrons that might cause light and matter interactions. And in fluorescence, likewise, many electrons are involved. That's why the emitted energy can belong to different colors, can belong to different, let's say, ranges. Here we can see one atom can emit blue color and green color, and the mixture can look like something like that. Okay, so in fluorescence, molecules absorb light, becomes excited, and while they are returning to their ground state, they emit light, and the emitted light has always lower energy and longer wavelength. As we talked in our previous lessons, the higher, the longer wavelength, the lower energy, the shorter the wavelength, the higher energy. So the emitted light in fluorescence has always lower energy level compared to the absorbed light. Okay, next. And here we can see I'm sorry. The next, here we can see that fluorescent compounds absorb shorter wavelength and emit light with longer wavelength. The shorter wavelength, the higher the photon energy again, which equals to energy. The energy equals to hc and divided by lambda. And we are going to talk about this equation in the coming pages. Energy, yeah, Planck constant, the concentration, wavelength. Okay, the point that we have to understand about the fluorescence from these images include that, as indicated here, the absorption energy has always shorter wavelength compared to the emission, as indicated here. That's why the intensity can also be lower compared to the excitation energy and absorption level energy. And here we can see that this is the ground state, the absorbed energy can cause the electrons to reach excited levels, S1 excited level, S2 excited level. And in fluorescence, we see the loss of electrons as the vibrational energy, and the remaining energy turns to emission, as we talked earlier. So these two figures tell us about the excited state that causes loss of energy, and the emission that has lower energy level compared to the absorbed energy. This is for one photon excitation fluorescence, and this is for two photon excitation fluorescence that can differ from each other by this. Okay, two photon excitation can look like this, and one photon excitation can look like this. Okay, and here we can understand these changes more in detail by using the electrons in singlet state or triplet state. Singlet states, a total of spin, angular momentum of zero, are denoted by an S. This S2, and S0 belong to singlet status, and triplet status, which mean a total of spin angular momentum of 1. Here we can see T1. This indicates excited triplet state. Okay, excited triplet state, and S2 and S1 means excited singlet state. And singlet state has this kind of electron spins, and this is excited state, excited singlet state. In excited English singlet state, we still have excited electrons, but they are still, let's say, paired. The spin is kept. But in excited triplet state, that differ from excited singlet state, we do not see the spin pair. Okay, this is about the differences in terms of singlet and excited triplet status, and what happens during the fluorescence has been well explained in this figure. The blue lines indicate the absorbance of the light or UV energy. Yeah. This is about the absorptions, which lasts about 10 to the power of minus 15 seconds. And fluorescence also have this kind of short time. I mean, even if it's kind of bigger, but it's still a small time that might happen between 10 to the power of minus 10, 10 to the power of minus 7 seconds. Okay, this belongs absorbance. That absorbance can happen from S0 to S1, or from S0 to S2. Yeah. And but fluorescence might happen from S1 to S0. And what happens between S2 and S1? So when the absorbance causes the electrons jump from S0 ground state to S2 excited state, some energy is lost as, let's say, this one, as a vibrational relaxation, as we see here. Yeah? Some energy might be lost as vibrational relaxation. Yeah, so some energy turns to another type of energy that could be released as heat or some vibration. Yeah, and also internal conversion can happen there, and after that, the remaining energy can turn to the emission. So emission happens between S1, S2, after some energy is lost or some energy is turned to vibrational relaxation. So this means some energy is lost, and then remaining energy turns to emission. That's why the energetic level, energetic capacity of emission is always of lower level compared to the absorption during the fluorescence. Okay, and the difference between fluorescence and phosphorescence is explained with these changes, even if it's not written here about the phosphorescence. This change belongs to phosphorescence, about which we are going to talk in some other figures as well. Some energy level can still be lost. Some energy can still be lost while the spin pair is lost. I mean, here we can see S1, excited singlet state. When excited singlet state turns to excited triplet state, okay, still some energy can be lost. So the fluorescence can still happen from the T1 level to S0 level, from the excited triplet state to the ground singlet state. So this is about what kind of changes are observed during the fluorescence. And here we can see that fluorescent compounds absorb shorter wavelengths and emit light with longer wavelength. The shorter the wavelength, the higher the photon energy. And the equation has been explained here. E stands for energy, H stands for frequency. I'm sorry, Planck's constant. Sorry, yeah. This Greek V stands for frequency. And since frequency equals speed of the light is divided by wavelength, yeah. So we can replace V with C over lambda. So then we can develop this kind of equation in which energy equals Planck's constant multiplied by speed of the light divided by wavelength of the light. The second formula is derived. This one is derived from the first by using the relationship between frequency, wavelength, and speed of light. And Planck's constant can look like, I mean, the energy equation can look like this. Okay. And here we can see the meaning of shorter wavelength and higher the photon energy. In our previous lessons, we talked to you about this phenomenon as the wavelength of the electromagnetic waves is shorter. So there is a general statement that their energy, photon energy, is higher. So when the matter absorbs blue light, for example, yeah, and it absorbs much energy, and some energy turns to vibrational relaxation, as we talked in this previous page. Yeah, that's why the remaining energy can be emitted as green color, or yellow, orange, or red color with higher wavelength, I mean longer wavelength or higher wavelength, and lower frequency with smaller, let's say, frequency and smaller energy. Okay, and in this photo we can understand this information, the information described here once again. Okay, from the ground state in which the electrons own the lowest energy, when they absorb some energy, the electrons jump from the ground state to the excited state. The excited states can be different, S1, S2, and S3. Here we have only one excited state, S1. Yeah, the lowest energy level where the molecules normally exist without additional energy. And S1 is the excited state in which higher energy belongs to the electrons, a higher energy state reached after absorbing light. And absorption is the process in which those photon energy is owned by the electrons. And molecule absorbs a photon and moves from the ground state to a higher energetic state and to higher electron orbital. And non-radiative transition happens here, as we talked in the previous pages, as a vibrational relaxation. And here this is about the non-radiative transition, and the remaining amount of the energy, and then turns to emission again. That's why the photon energy level of the emission is always lower than the energy level of absorption, because of the energy that's lost as a non-radiative transition. Okay, and fluorescence, the green arrow shows fluorescence here, and the molecule returns from S1 to S0. Light is emitted at a lower energy with longer wavelength, with smaller frequency. And here we can see some theoretical calculations about the energetic levels. Fluorescence occurs when an electron absorbs light. So when light is absorbed, what happens? The molecules occupy highest occupied molecular orbital, as indicated here, which is abbreviated as HOMO, highest occupied molecular orbital. And when those electrons fall back to their ground state, those molecules own the lowest unoccupied molecular orbital, as indicated here. Here, these electrons have higher, let's say, occupied molecular orbital among these three atoms, as indicated here. When they fall back to their ground state, reverse. So the higher electron orbitals can happen between them, yeah, as indicated here. So this is about highest occupied molecular orbital, which explains the absorption, and this is about lower unoccupied molecular orbital, which explains the emission of the light, and subsequently release energy returning to the ground state when the occupation of electrons turns from this size to this size. Okay, we witness the emission. The HOMO-LUMO energy gap determines the emission wavelength. A smaller gap results in a longer wavelength. As we talked, if the vibrational relaxation energy has a smaller volume, I mean smaller level. Yeah, so then the difference between absorbed and emitted light is expected to be a small unit. If the vibrational energy level is high, so the difference between them, between absorption and emission is expected to be high enough. Okay, next. Okay, and here we can see the excited energy level and emitted energy level. Excited, let's say, spectrum when the electron absorbs photons, and this one uh, full line stands for the emission in different three compounds termed as GFP, green fluorescent protein, and E2 orange as indicated in orange color, and M cherry which is indicated in red color. So we can see that the emission level is always of smaller energetic level because of the longer wavelength, since some energy during the fluorescence is lost as vibrational relaxation. So what we have to understand from these two figures is that between the excited and emitted states, there are overlapping areas, as shown here. And another point is different compounds, different molecules have different emission peaks, okay, levels. Next. And there are many factors that affect the fluorescence. Now we are going to talk about those factors. They can be molecular structure, solvent polarity, temperature, pH, media, and some other factors. The first one, as you see, is molecular structure. Since molecules have different structures, their fluorescence can differ from each other as well. Emission spectra obtained using 532 nanometer excitations are appreciably overlapped with maxima at 535 nanometers for R560, R123, and AZ, and 551 nanometer for R6G, as indicated here. Yeah. Uh, and 558 nanometers for QD, yeah, as indicated somewhere here, and 574, yeah, not big differences between them for the RB, this one, the red one. What we have to understand from this figure is that let's take two similar to each other figures like R123 and RB. These two compounds differ from each other by methyl group and hydrogen between them at this position. And here NH2 and NH2 positively ionized and differ from this compound by the ethyl groups exchanged with two hydrogen in this position and two hydrogen in this position. And the addition of four ethyl groups and the exchange of this methyl group with hydrogen uh, causing lower energy and higher wavelength of this red colored compound. Here we can see the peak of green color belongs here. The emission has this kind of area, and in green color compound, in the red color compound, different from this by ethyl groups, have this kind of shift compared to yellow one. Yeah, and another example can be this color and black color. I don't know the name of this color. How do you call this? Is blue violet. I don't exactly remember its name. So R560 and R6G differ from each other by the absence and presence of ethyl groups. Yeah, one hydrogen has been replaced with ethyl group, and here another hydrogen has been replaced with another ethyl group, and similarly here we can see the exchange of this hydrogen with ethyl group. So the addition of three ethyl groups is causing another shift, but it's not as remarkable difference in this case. But here there is significant difference between the peaks of these two compounds. So the addition of ethyl groups is causing the shift of this emission level from, let's say, from 535 to somewhere, 551 and 535, and something like this. Okay, I'm sorry, from 535, it is coming to 558, something like that. Okay, the point is, okay, there is a shift because of the addition of ethyl groups. So the point we have to understand in this case is that molecular structures and the presence of different functional groups are the factors affecting the fluorescence level of compounds. And the second factor is solvent polarity. Here we can see the structure of Nile red. Nile red has its own fluorescence when it is dissolved in different kind of compounds, different kind of solvents. They tend to change the fluorescence range and the intensity as well. In this case, we see the fluorescence shift in different solutions. In hexane, it has this kind of wide range of fluorescence. When it is dissolved in toluene, it has this kind of area, and chloroform, it has some area around the orange color, and in acetone closer to red. And when it's dissolved in methanol, the fluorescence level is around the red color as indicated here. What we have to understand, when it is dissolved in water, we can see it is shifting to level to nanometer closer to 600, let's say 75. What we have to understand is that as the polarity of the solvent is increase from hexane to water, here we can see in C example in the unnormalized emission, here we can see the level of the intensity is lower and lower in many cases. It's not something linear, but in case of chloroform, methanol, toluene, chloroform, acetone in methanol, and we can see the lower and lower, let's say, values. Toluene can be exclusion here. And let's look at the level of water, and water is almost completely preventing the fluorescence level of Nile red when it is dissolved in water. And similar changes were observed in cholesterol, sulfatide, as phospholipid when Nile red was dissolved in either of them. So what we have to understand from these results is that the solvent polarities is another factor that affects the fluorescence of compounds. And the third factor is temperature. Here we can see the fluorescence intensity of which compound is it? Fluorescence intensity. Okay, PSNB2. I didn't provide the full name. The fluorescence level of this compound, you can find out about that, about those results in this figure. That the fluorescence intensity is increasing as the temperature is, fluorescence level is decreasing as the temperature is increasing. The higher temperature, the lower fluorescence intensity, the lower temperature, the higher fluorescence intensity. At 0 centigrade is indicated in here in black line, 298 Kelvin. Yeah, here we can see the highest level of fluorescence when the temperature has been increased to 50 centigrade. Yeah. 50 centigrade to 348 Kelvin, the fluorescence level of that compound has almost disappeared, as we witnessed here. And here we can see another example, gold nanoclusters, glutathione capped gold nanoclusters, uh, which indicated highest fluorescence intensity at 0 centigrade, and at 90 centigrade it almost completely prevented at higher temperature. So here we can see this kind of lower and lower lowering tendency of the fluorescence level as the temperature increased from 0 to 90 centigrade. So more than, let's say, more than 10 times differences were observed between the fluorescence level when the temperature ranges from 0 centigrade to 90 centigrade. Okay, next. And the next factor that affects the fluorescence is pH media. In these examples here, we can see the examples. In this case, okay, at 5 pH, here we can see this kind of results of the fluorescence here. Let's say lower at pH 9 compared to pH 7. In both cases, in intensity and lifetime. And this is not very, let's say, clear as in pH 7 and 9. So this is one example. And another example is given here. So here we can see the effect of pH lowering from 10 to 2. Here we can see at 10, at pH 10, here we can see the highest level of fluorescence intensity as the pH is lowering to 2. Here we can see almost disappeared level of fluorescence. And here we can see, let's say, as the fluorescence, as the pH reduce it from 10 to, let's say, 6 or 4.5. The fluorescence intensity lowered 2, 3 times respectively. Okay, this is about the effects of pH on the fluorescence level. Here, here we can see the differences in absorption maximum at 458 and 488 as indicated here. And another factor that affects the fluorescence level is reactive oxygen species. Not only reactive oxygen species, but also reactive hydrogen, nitrogen species can also cause the differences in fluorescence level, because these are the compounds that affect many chemical and biological processes in cell life, in cell biochemical processes. So here we can expect similar changes by the reactive oxygen species as well. Here we can see that the concentration of hydrogen peroxide increased from 500 to 2000. Here we can see 2-3 times, let's say, more intense color of green color as indicated here in 3 days. but those differences in 7 days did not differ as in 3 days. But anyway, what we have to make a conclusion is that the higher concentration of hydrogen peroxide resulted in the more bright, let's say, green fluorescence in those conditions. And similar differences were observed in the adults of Encyptraus crypticus. These results were observed in cocoons, and these results were observed in adults. So the reactive species are in other types that might affect the fluorescence level as well. And these are the examples that help us to understand the fluorescence, the mechanism of fluorescence. Once again, this diagram is linked with Perrin and Jablonski. Often it shows possible radiative transitions of absorption, fluorescence, and phosphorescence. And we have to understand the difference here between fluorescence and phosphorescence. Okay, ground state, energy, electrons were excited and given some photon energy. They shifted to S1 or S2 excited status. And from the S2 excited state, by losing the energy as vibrational relaxation, the electrons fall to S1 level, and in S1 level, the further energy loss is explained with the emission. So the some amount of the absorbed energy is emitted, as indicated here. Yeah, we call it fluorescence, but there is another process we call it phosphorescence. What is phosphorescence? Phosphorescence is the emission after the intersystem crossing, ISC, when the electrons turn from singlet excited state to triplet excited state. Again, some vibrational energy can be observed here, and the remaining amount of energy remaining amount of energy turns to emission, and after the changes between singlet and triplet electrons, we call this emission as phosphorescence. Okay, here we can see this is absorption from S1 to S0 to S2, and this is also absorption from S0 to S1 as indicated here. Yeah, and this is fluorescence from S1 to S0, and this is phosphorescence from T1 to S0. So the what is phosphorescence? Phosphorescence is the emission from T1 to S0, and fluorescence is the emission from S1 to S0. Okay. Fluorescence and phosphorescence are types of molecular luminescence and luminescence methods. A molecule of analyte absorbs a photon and excites a species. The emission spectrum can provide qualitative and quantitative analysis. The term fluorescence and phosphorescence are usually referred as photoluminescence because both are alike in excitation brought by absorption and photon. The point we have to understand is that fluorescence and phosphorescence are types of molecular luminescence, and luminescence processes are linked with the jumping and falling of electrons from the ground state to excited states and excited states to ground states, respectively. Okay, fluorescence differs from phosphorescence in that the electron energy transition that's responsible for fluorescence does not change in electron spin. And we are going to talk about this a bit in the coming pages, which result in short-lived electrons and in the excited state of fluorescence. So the difference between fluorescence and phosphorescence is explained with the presence and absence of electron spins. In phosphorescence, there is a change in electron spin, which results in a longer lifetime of the excited state. Fluorescence and phosphorescence occur at longer wavelengths than the excitation radiation, as we talked earlier. And here we are going to see the differences between fluorescence and phosphorescence. The fluorescence is a kind of shorter period. It occurs in 10 to the power of minus 9 seconds, nanoseconds, and phosphorescence lasts for milliseconds. So the duration of phosphorescence is much longer, several times longer compared to fluorescence. It involves singlet-singlet transition, as we talked here. Yeah, singlet-singlet transition in fluorescence, and singlet triplet transition in phosphorescence. Actually, in phosphorescence, from S1 to T1, yeah, from singlet to triplet, and then from triplet to ground state to singlet, yeah, ground singlet state. So this is the point that differ from the fluorescence. And energy loss. Fluorescence emits higher energy light, minimal non-radiative transition. And in phosphorescence, we witness higher non-radiative transition. So the wavelength of the phosphorescence is expected to be longer than the wavelength of the fluorescence. And about the visibility, fluorescence visible only when the excitation source present. And in phosphorescence, we can observe the emission for a time, even if the light source is not present. Yeah, because it can last longer. An application. Fluorescence is used in microscopy, flow cytometry, fluorescence spectroscopy. Yeah, we talked about this microscopy and fluorescence spectroscopy in this and previous lessons, and hopefully we will talk about flow cytometry as well. And in phosphorescence, it is mainly used in safety science, time results spectroscopy, and oxygen level sensing. Let me remind you. Let me remind you, safety science of policeman, yeah, who works at night. Okay, if there are no the sources of light, um, in order to be seen in distance, the policemen are provided with the phosphorescent phosphorescent dresses. I mean, their dresses are provided with phosphorescent compounds to be noticed in long distance. Okay, so these are about the differences between fluorescence and phosphorescence, and here we can see the differences between them as well. In fluorescence, okay, the duration is nanoseconds, as we talked, 10 to the power of minus 8, 10 to the power of minus 9 seconds. And in phosphorescence, it can be minutes or it can be hours. And here it was said milliseconds. Okay, in different compounds that have phosphorescent property, okay, that can differ. And in some of them, like phosphor, okay, that emission can last hours as well, or minutes at least. And electronic transition, again, in fluorescence, singlet to singlet, as indicated here, from singlet to singlet in vibrational relaxation, and even in the fluorescence from singlet to singlet, from S1 to S0. And in phosphorescence, first intersystem conversion happens from excited singlet to excited triplet, and then from excited triplet to ground singlet type of electron or orbital. Okay, and there are no spin flips in fluorescence, spin changes, and in phosphorescence, there is a spin flip uh, from singlet to triplet, from triplet to singlet. Yeah, and what happens if light source is taken out? Okay, in fluorescence, okay, it stops fluorescing, yeah, and phosphorescence can still continue even if without the light source for some time. That could differ from minutes to hours. Okay, in order just to understand the whole meaning of singlet, doublet, and triplet, here we can see that singlet is with no unpaired electrons as indicated here, yeah? And doublet is with one unpaired electron as indicated here, and triplet is two unpaired with two unpaired electrons. And this can provide a more, let's say, comprehensive description. This is ground single state. Difference between ground single state and excited single state is about the presence of spins. Here, the spin is preserved between the ground and excited states of a singlet electron. But in triplet state, as we see here, there are two unpaired electrons with no spins. Yeah, the spin pair has been changed here, and here we can see this kind of single pairs here in singlet and excited status, but in triplet state they are not spins to each other. So the difference between fluorescence is about singlet and triplet states of electrons. And this is another example about the fluorescence. Fluorophores are the compounds that absorb light at a specific shorter wavelength that we call excitation and re-emit it at a longer, lower energy wavelength that we call emission. The point is when the fluorophore compounds are linked with the target molecules, okay, we can expect and observe and strong fluorescence after their linkage. It's not very strict in some cases because of the linkage of the fluorophore compounds by the breakage of carbon-carbon double bonds. Okay, we can expect some lower fluorescence level as well. But in most cases, as expected, okay, the linkage of fluorophore compounds with the target molecules, okay, we expect the strong fluorescence. And this is about green fluorescent protein, which is used in cell experiments a lot. It is rich in lysine and F. F amino acid, phenylalanine. I couldn't find its name. Phenylalanine and lysines are rich in are a lot in the composition of green fluorescent protein. And why green fluorescent protein is used a lot in cell experiments is described here. It is okay. Human eye is quite highly sensitive to green light, differing from 500 to 550 nanometers. It produces bright and easily detectable signals, and reduced overlap. I mean, the low background interference is reduced, and it overlaps with cellular antifluorescence, and it results in clear images. And they are kind of safe with provided with reduced phototoxicity. They require moderate excitation energy, safer for live cell imaging. and they are highly photostable. They are resistant to photo-bleaching agents. They are suitable for long-term observation, and they can be genetically linked with some proteins. Some proteins can be fused with the total sequence of these amino acids, or some fragments that could provide the fluorescence for those proteins. So in genetic engineering, they can be effectively used. And another reason is that most microscopes are optimized for the green channel, and they are easy and reliable for the detection. Here we can see some examples of a GFP, yeah, green fluorescent protein. This is in cytosol, this is in endoplasmatic reticulum. This is in mitochondria and plasma membrane. Yeah, subcellular localization of green fluorescent protein and green fluorescent protein fused organelle and markers targeted to different organelles of rice protoblasts. So what we have to understand from the figure is that green fluorescent protein can be linked with some targeting molecules. They could be some small sequence of amino acids by providing with targeting molecules. Again, those proteins can be targeted to some organelles to see their localization. For example, here we can very well see the localization of hundreds of different, let's say, mitochondria. Yeah, without green fluorescent protein, okay, we wouldn't be able to see those targeted molecules. For example, by after fluorescence, okay, we can develop this kind of images, or by bright fields, we can develop this kind of images. But by using the fluorescence, green fluorescent protein, we can develop this kind of images that can enable us at least to know about the localization of the subcellular organizations. Okay, subcellular organelles. And this is another example. Here we can see the endoplasmatic reticulum, yeah, by the green fluorescent protein. Yeah, by the combination of green fluorescent protein and chlorophyll autofluorescence, we can develop this kind of figures. So green fluorescent protein is something that could not only reveal the localization of some subcellular organelles, but also enrich the images when combined with other methods. Yeah, this is the merged ones of green fluorescent protein and chlorophyll autofluorescence. So these are the examples to green fluorescent protein utilization in some cell experiments. And this is another one. Here we can see the mitochondrial targeting of green fluorescent protein and loss of mitochondrial membrane potential in those examples. Okay. Mm, we can by obtaining this kind of figures, okay, we can have uh, clear images that could enable us to see the localization again, and the distribution of some organelles, or some cell processes can also be, let's say, detected by using green fluorescent protein. Cell division, for example, can be quite well described by using some proteins that could target chromosomes as well. Okay, and this is about, I think this is the last page. This is about the differences between fluorophores and chromophores. Chromophores absorb light only to show the color, and fluorophores not only absorb light, they also re-emit. So the main difference between fluorophores and chromophores is about the re-emission. In fluorophores, we observe re-emission, in chromophores, we do not. And okay, we talked about the emission, and overlapping can be observed in fluorophores, yeah, and in chromophores we do not observe it. And the purpose, fluorophores are used for bioimaging and sensitive detection, and chromophores are used for colorimetry. Chromophores are used for quantification, yeah, not only in colorimetry but also based on the chromophore groups, we can quantify some compounds by using HPLC as well. And fluorophores often have rigid structures. Yeah, fluorophores often have rigid structures to promote emission over heat loss, which is not required for all chromophores. And green fluorescent protein or phenyl isothiocyanate is an example for fluorophores, and these are other examples of fluorophores. And chlorophyll is an example to chromophores. Here we can see some other examples to chromophores. Okay, the main difference between fluorophores and chromophores results from the re-emission of the light. Okay, these are all. I express my thanks for your attention, and I kindly ask you to support us with your likes, and I ask you to share the YouTube link for these videos with your friends, so that these lessons can reach a wider audience. Thank you for your attention and have a good day. Bye.